Okay, so welcome to the Spring 2024 A2 sessions. This is session 1 with myself, Mr. Black, teacher at e-sgol Penglais in Aberystwyth, and I'll be going through accurate enthalpy change calculations, specifically how they're measured and how you construct your Hess cycles for those. Okay, so let's get started then. So this is actually, although a year 13 session, so practical from year 12, as you can see, it's from the AS unit. However, you have to remember that your examinations this year will have a practical examination, and you will be expected to recall practicals from year 12. So let's get into this practical then. It's an indirect determination of an enthalpy change, and it's the reaction between magnesium oxide and carbon dioxide to form magnesium carbonate. So I'm just going to give you a moment there. So I like you to work things out as you go along. Little pause, write the symbol equation for that reaction. Okay, and hopefully you came up with something like that. So what we're going to be doing is we're going to be looking at this enthalpy change and determining its value. Now there's a problem. This reaction is slow and the enthalpy isn't that big, so you're not really going to be able to record this experimentally. I'm afraid a polystyrene cup with a thermometer in it isn't going to do the job for us. So how are we going to find this enthalpy change? Well, we're going to use, obviously, Hess's law. Okay. Now, massively important, you know, you've got your, it's 3.7, 3.6, lots of thermodynamics in there. Make sure you do know how to talk about Hess's law, have a good definition for it, have your own. I've just quickly got one off the internet. Enthalpy change, chemical change, is independent of the route by which the chemical change occurs. In my own definitions, I actually say the enthalpy change is the same, okay, independent of the route taken. But get your definition, make sure it's a good one. Good place to look is always mark schemes. Okay, so we're going to have to construct a Hess cycle. So we're going to have a quick look at the format that we would use for doing that. So you can see here, this is the kind of Hess cycle we would be using. And you can see that I've got my arrows pointing down, and the direction of these arrows are hugely important when you construct your Hess cycle. You have to reflect, you know, the enthalpy change, whether you're going from reactants to products or vice versa. So please make sure that, you know, you consider this, and we will be doing that as we go throughout the this practical. So we're going to construct a Hess cycle, and this is really important, this idea here, these intermediaries, because they kind of determine what your Hess cycle is going to look like and how it's constructed. Okay, so let's consider our reaction. We're going to try and work out this enthalpy change, and we're going to use two different reactions to help us do that. Okay, reaction enthalpy change for reaction A and enthalpy change for reaction B. So we're going to think about what our intermediaries will be. So it's obviously, before we carry on any further, it's probably worth saying to you, it might be a good idea to actually look at this practical in your practical book and make yourself familiar with it. So kind of like you're not coming from a blank slate. And you may even look at that practical book now and go, do you know what? I don't need any help with it. But however, if you do need help with it, then that's what we're going to be going through now. Okay, so there's the reaction. And if you go to the practical book, you'll see that the apparatus and chemicals we need are here. Specifically, though, for us in constructing our cycle, it's this bit here. So it looks like we've got our dry magnesium oxide. Okay, it's important because we don't have any water in there in terms of mass. And we've got some dry magnesium carbonate. And you can also see that we've got some 2 molar hydrochloric acid. Okay, fantastic. So why is that going to be useful to us? Well, let's consider then what's going to be happening. We're going to measure this enthalpy change. I'm going to be using a calorimeter, which sounds posh, but typically in year 12 it isn't. It's going to be a polystyrene cup with your reaction taking place in there. And you see this word here, system, dissolved in water. System, remember, are your reactants and your products. So it's referring to the actual reaction that takes place. not the water that they're taking place in. So this is the kind of setup we'd use to measure an enthalpy change for an aqueous reaction, one that takes place in water. Okay, and effectively what we're going to be doing is we're going to measure how much heat is raised in the temperature of the water by adding the 2 molar hydrochloric acid to some magnesium oxide, measuring that temperature change, and then we're also going to do that with some magnesium carbonate, and we'll measure that temperature change, and then we'll be able to calculate our enthalpy changes for those two reactions. Okay, so let's look then at the actual reactions themselves. Okay, and that will kind of help us work out what our intermediaries are. So we've got the two reactions here. We've got the reaction with the magnesium oxide hydrochloric acid and the magnesium carbonate hydrochloric acid. So again, I am going to pause because I want you to do a bit of work. I want you to obviously write out the products of those reactions and then balance them up. Okay, so I'm going to carry on now. You see in our first reaction, we've made salt and water, which is what we expect with a base and an acid. And we'll just balance that up with the two there. And then in our carbonate and hydrochloric acid reaction, again, we get our salt, and we get water and carbon dioxide. Let's think about our intermediaries. What's our common thing that links both sides of our equation? Well, hopefully you can see it's these products here, specifically the magnesium chloride. So now if we look, we can see that magnesium oxide would form magnesium chloride and water. The carbon dioxide would be unreacted, so just be carbon dioxide still. The magnesium carbonate would actually form magnesium chloride, water and carbon dioxide. So those are the intermediaries. Notice the arrows are pointing to them. These are formed in the reactions, so that's why the arrows point to them. Okay, so we've constructed our Hess cycle. All we need now is our values on the arrows. Okay, so how are we going to do that then? Well, we're going to use this equation here. So hopefully you should be familiar with MCAT. So we've got this delta Q. Now Q, what is Q? Well, that's the energy change, all right? And this is basically the energy that change in the water. So you can think of the system as being, you know, the reactants and products. And you can think of the water that the reaction's taking place in as being the surroundings, all right? And we can see that, you know, when we do this reaction, that they're both exothermic reactions, and the temperature of our water is going to go up. Okay, and that means therefore we're going to work out by how much energy has been released to cause that temperature to go up. And we use this equation here, MCAT. Okay, so we're going to think about these values and where we're going to get them from. Well, first of all, we need to know what Q is. So I've said that's our heat energy, change of the water. The M is the mass of the sample in grams. Now we have to be very, very careful here. And then C is our heat capacity and delta T is our temperature change. And we'll be looking at how we do that accurately in a moment. Okay, so once we've worked out our delta Q, then we can convert that into our delta H. And there's a difference between delta Q and delta H. Delta H is our actual enthalpy change, and that's the change in the enthalpy of the reactants to the products. All right, and it's in per mole. So this value isn't per mole. This is just literally how much heat the temperature of water raises by from our reaction, and then delta H is per mole. Okay, you can see here I've put a minus Q on this. This is because obviously as temperature goes up, i.e. exothermic reaction, the enthalpy of our system has actually gone down. So that's to reflect that kind of inverse relationship between the two. Okay, we are going to look at another way we can do this bit of a calculation where we combine both these into one. So we're going to look at the values then for working out the change in the heat energy of the water. We're using our MCAT. So let's think about M. What is M? So it says it's the mass. Well, mass of what? Well, it's the mass of solution. Okay. So we've got your hydrochloric acid here. If we look in our method, we've got 50 mil. All right. So what we assume is that this is the 50 mil is well, it's all water. It is all water. That has some hydrochloric acid dissolved into that 50 ml of water. Okay. What we don't include in here is the mass of the solid. All right, and that's a really common mistake that I quite often see. So people, when they're putting M into this calculation, they would write it as 50.90, and it's not. You do not include the mass of any solid. It's literally the mass of solution. Okay, and hopefully you know the density of water is 1 gram per centimetre cubed. Okay, so we know that that's going to be 50. The C, well, that's our heat capacity. Usually they'll quote it on the question for you. If they don't, then it's on your data book. Don't mix it up with the speed of light, by the way. You're going to get quite a lot of energy increase in the temperature of the water. So yeah, don't confuse those two, obviously. Okay, and now we're going to look at delta T. So delta T is the tricky part here, and it's the part that I want to make sure that you've got your understanding of how to get that value accurately. All right, so there's the method we use to actually measure our delta T. I'm just going to give a little pause, so you can pause and have a quick read, or you can look for your own experimental book. Okay, so you've read there then hopefully that initially you don't actually measure the temperature of the reaction. You literally put your thermometer in for 30 seconds and you just measure the temperature of the acid for 2 minutes and 30 seconds. And then you, at 3 minutes, you then add your substance, the magnesium oxide, in this case the acid, and you still don't measure the temperature, which is kind of weird, right? What you're doing at this point is you're just making sure they're mixing thoroughly. Okay, so you want to make sure you get the reaction releasing all its heat as quickly as possible. And then you start recording your temperature again at 3 minutes and 30 seconds. Okay, so you've had a little pause where you haven't taken any temperatures. You start recording temperatures again, and you do that for about another, well, I think it goes up to about 10 minutes. Okay, it's up to you. What they said, continue record temperature 30 seconds until the temperature drops to 5 consecutive readings. Right, there you go. Okay, so once we've done that, we've got some data here. So this is off the WJC, and we've got our mass of our magnesium oxide. You can see here that they've done a weighing by difference. And if you don't know about weighing by difference, I have done another practical run through that might be of use to you as year 13s. It is a year 12 practical, which I think I've done on the spring 24 sessions, which is our session 2. So you might want to go and have a look at that. I'm not sure, it might be useful to you. Yeah, it's the practical I ran through the year 12s. It was gravimetric analysis, and I talk about, you know, the importance of weighing by difference. So we've got a mass here of 0.921 grams, and you can see here we've recorded with a thermometer that's got a resolution of 0.1. We'll talk about resolution later. And you can see here that temperatures remain fairly static, as you'd expect, coming at the bottom, nothing being added to the reactant, to the hydrochloric acid. There's a blank here because we're not recording temperature, and then we have every 30 seconds temperatures recorded. Okay, so you can see they've gone up to 9 minutes with theirs. So what do we do with this? Well, we plot a graph. And this is really important that you know how to do this. A couple of things I'm going to point out to you. First of all, temperature has not started at 0 on this axis. If you started at 0, which I see people do when they first draw this graph, all your points are going to be at the top half of your graph paper. You're not making good use of the graph paper, and you'll lose accuracy in plotting your points. So please make sure that you plot your graph or do your axes and don't start at 0. Start at the, you know, the temperature just below your start temperature. Okay, and you can see here what we've done is we've drawn lines of best fit for these points. Okay, and we've drawn a line of best fit for these points here. Okay, and we're going to look at these graphs now. We're going to practice drawing them. We'll come back to this graph in a moment when we come to do our calculation, work out our delta T and so on. So we've got some practice ones for you to have a look at. You can see here, I'm just going to get rid of that line, skipped ahead. So I've got some points here for you to kind of have a practice on. And you see here, this is an exothermic reaction. There's been a rise in temperature of the water. And we're just going to put our line of best fit for those points there. Oops, going backwards again. We're going to put a line of best fit for those points there. And we're going to also put a line of best fit for those points there. And then what we're going to do is going to find our delta T. Now we're going to assume there's no point at 4 minutes because this is when we're mixing our reagents. So our delta T is going to be at this 4-minute mark. And to find delta T, all we do is we draw a line between the 2 points, to the 2 extrapolated lines. And then we read off our values from here and our value from here on the temperature axis, and we can find our delta T from there. If you go back to the original graph, you can see that's exactly what we've done at 3 minutes. Whether you weren't taking the temperature, they've actually drawn this line between these 2 extrapolated lines here. Okay, and that's where they'll get their delta T from, as we'll see in a moment. So, got some more ones for you to look at. What kind of reaction is this? Well, hopefully you recognise this as being endothermic. We see there's been a decrease in temperature, and I just want you to think about what the lines, extrapolated lines, might look like here. Okay, so that's pretty straightforward to do. And then this line here is drawn this way. And the way that I want you to think about drawing these extrapolated lines and your line of best fit is your main kind of where you know the steady increase or decrease in temperature is going to be from the points furthest from the mixing point. So what I've done is I've given preference to these points when I've extrapolated, drawn my line of best fit. Okay, so precedence here, less precedence over here. These, we can see that temperature hasn't fully decreased. Maybe the reaction hasn't fully kind of taken place, or maybe the temperature hasn't kind of, caught up with the thermometer. Who knows? But anyway, we'll extrapolate for those points. And then at 4 minutes, my mixing point, draw a line between the 2 extrapolated lines, and that's your delta T. There we go. Okay. So some more for you to just have a quick look at. I'm going to do a very quick pause for you so you can perhaps have a think about what those lines might look like. And now on the next slide, we should see these lines coming in. Okay, there we are. So that's what I've done. You can see how I'm ignoring these ones here. I'm ignoring this one here. I'm ignoring this one here. And I'm ignoring these here. Okay, so as long as you kind of show that awareness. So let's go back to our graph then. So one of the things I want to point out to you then is when we've drawn these lines, notice these 2 points here, they have been completely ignored. Okay, they're not fitting in. So basically what you can tell here is that the reaction is still taking place at 3.5 minutes, and it's still taking place at 4 minutes, hasn't released all its heat yet. By 5 minutes has released all its heat. Okay, right. Okay, so what we're going to do next then is look at our axes. Always check your axes, what we're going up in. So we're going up in intervals of 1. No, not. Yes, we are going up in intervals of 1. And there's 5 squares in between each interval value. So that means we're going up in 0.2s. Okay, so 23.2 is our start temperature. We come to axis here, and we come across, and we're exactly at 37.0. Notice, by the way, I haven't put 37, I've put 37.0. Okay, so that gives us a delta T of 13.8. So next we go now to our calculation. We're going to work out the change in heat energy of the water. And that's our calculation. So the 50, remember, is the volume of the hydrochloric acid. The 4.18 is the heat capacity, and our delta T is our accurate temperature change. And that gives us a value of 2,884.2 joules. In joules, by the way, because heat capacity, if you notice on your data sheet, that's in joules per gram Kelvin. Okay. So we're now going to think about the enthalpy change, because this is the energy change of the water. And what we want to know is the enthalpy change of our system. We know this is an exothermic reaction. So we know there's going to be a decrease in enthalpy, hence the increase in temperature of water. Okay, and what we're going to do now is we're going to convert this into our delta H. So the first thing I've done there to reflect that kind of, difference between change in temperature of the water and the enthalpy change of the system, we're going to minus Q our value. Okay, so it's going to become minus 2884.2, and then we divide by N to scale it up to per mole. Okay, so working at N, we need to go back and look at the mass that was used here. So we used 0.921 grams. So I'm just going to give you a moment to work out the number of moles of the magnesium oxide. And I'm going to carry on now. So you've got 0.0229. So we're going to now plug our values into our calculation. I can see there, that's our first enthalpy change. So we've got an enthalpy change of 126 kilojoules. Great. Okay, let's go to our quick calculation here. Now, this is the quick way of doing delta H calculations. It's a combination of the energy change of the water, i.e. Q, and also it's the fact that the enthalpy change is the inverse of the temperature change or energy change of water, and then we're scaling up to per mole. So we kind of combine both into this one calculation. Now I'm going to talk to you about N. N is obviously the number of moles of substance, and you may ask yourself the question, well, what do we use as N? Do we use the moles of acid, or do we do the moles of magnesium oxide? Does it matter? Well, it does actually matter, absolutely. The N, number of moles of substance, has to be the substance that isn't in excess in the reaction. So let's just consider our reaction. Hydrochloric acid and the magnesium oxide. Okay, so those are the moles of the hydrochloric acid. This, by the way, is the concentration. This is our volume in decimeters cubed. And we've got 0.1 moles being used. And then we've got the moles of magnesium oxide. And you can see here that, well, we did this earlier, that we've got a lot less moles of magnesium oxide. But we'll just look at the equation. Okay, and we'll just consider, who's in excess. So if I had 0.0229 moles of magnesium oxide, how many moles of hydrochloric acid would I need? Well, the Bounce equation tells it's a 1:2 ratio. Okay, so we'd need double that amount, but we've got plenty. All right, so the minimum amount we need, or stoichiometric amount, would be near 0.0458 moles. Well, we've got pretty much, well, over double that. So it's definitely don't want to use this value as N. And that is something that you may be asked in examinations. I have seen them ask you which value to use, so which ones are not in excess. Right, so there's our Hess cycle. Okay, those are arrows. We've just got our first arrow. So we've got a value here now for 126 kilojoules per mole. So we're going to now go to this arrow here. And we're going to work out this delta H value. And so we've got there then. There's the data. And if you wish, it might be worthwhile you getting yourself some graph paper. You can always pause the video, come back to it in a moment, and plot that graph for yourself. And perhaps you could even work your way through the whole calculation yourself. Who knows? Okay, so obviously I've done that for you. So there's our graph. Okay, and you can see again we extrapolated our points. You'll notice again, look where the preference for the line of best fit points are. They're here, not this end. Okay, so whenever you plot your point, your line, and extrapolating, kind of do it through these points here rather than through those points there. Okay, and what we're going to do then is work out our delta T. And we use this expression here once we've got our delta T. It's the shortcut method, which is absolutely fine. As long as you're not asked to work out the energy change, then you can just go straight for this and work out the enthalpy change. Okay, so the value for N in our calculation, we've got our mass of 3.489, and we divide by the MR of the magnesium carbonate, 84.3. That gives us 0.0414 mole. Now delta T, we can see delta T here. We're starting at 24, according to our extrapolated line of best fit. And then what we're going to do is we're going to just focus in on this point here, so it's quite hard to read. And what would you call that then? What's the maximum temperature reached? So checking out what we're going in, say interval of 1, 5 lines between the intervals, so that means each line is 0.2. So I'm going to go with a value of 33.1 on that. So now we've got our delta T. So delta T is 9.1 degrees. Fantastic. Right. Calculate your delta H for me, just quickly, if you could. You say you could, if you wish, work out the energy change of the water, or simply the energy change, which is your MC delta T, or you can go straight into your delta H, where you do minus MC delta T over N. Entirely up to you how you do that. Okay, so let's have a quick look. There's our delta H. Okay, again, it's in joules, so don't forget that value is actually in joules. So really want to convert it into kilojoules. So now we've got our next enthalpy value. Okay, so what we've done now, then we've looked at experimental techniques for measuring these enthalpy changes accurately, and we've also constructed our Hess cycle based on the reactions we've got. Okay, so how are we going to use our Hess cycle? Well, hopefully, as you know, what Hess's law says, it doesn't matter what route you go, the enthalpy change would be the same regardless. So instead of going the direct route, we're going to go our indirect routes, which is this way. Okay, and then what we do when we go follow our indirect route, we simply then add our enthalpy values together. However, if we go against an enthalpy value or an arrow, we reverse the sign of the enthalpy value. Okay, so if you have a look at our delta H, you can see minus 126 plus 45.9, because we're going against the arrow, and that gives us an enthalpy change now for the reaction of minus 80.1 kilojoules per mole. So there's your Hess cycle constructed. Just download that off the internet as a little extra. Okay, and what I'm going to talk about now then is the issues of this experiment. Okay, so we're going to look at the accuracy, and accuracy is really talking about how close your value is to the actual value. So we've got our enthalpy change as minus 80.1 kilojoules per mole. And if we look at the actual value, it's actually minus 100.7 kilojoules per mole. So again, I'm just going to do a little pause here. I'm going to ask you to think about what the issues might be here. So why is our value lower? What could be happening? Okay, well, the most obvious thing that you would want to talk about in the exam for this experiment is the fact that heat escapes from the water. Okay, so instead of the heat energy passing into the water, being stored in that water, that heat energy can escape from the water. So what's our workaround? What can we do here to prevent this from happening? So what's a really good improvement to this experiment? Well, hopefully you've come up with the idea of putting on a lid, and that'll stop a lot of the heat escaping. By the way, they've used styrofoam cups here because obviously styrofoam is a good insulator. It keeps that heat energy in. Right, so that would be one thing that might cause our accuracy to be a bit lower than we'd want it to be. There's another issue as well that could explain why we're not getting as much heat as we'd expect, and that's to do with the number of moles that we've used. So if we've used 0.414 mole, we'd hope that all 0.414 mole would release all of its heat, but that may not happen. You may get that some of that heat, some of that might be impurities in the magnesium carbonate, hopefully not. Remember we talked about it being dry magnesium carbonate? Maybe there's a bit of water in there, so we haven't actually got as many moles of magnesium carbonate as we actually think we have. It could be that there's incomplete reaction, so you may not have some of the magnesium carbonate actually reacting. We just don't know. Okay, so that could be another factor, that you have incomplete reaction of the magnesium carbonate. There could be impurities in the magnesium carbonate. That would also give you a lower value for your delta H. Okay, so the other thing then that we're going to look at today, which is quite important for you, is estimating percentage error and why that's important. So we need to consider wherever we've weighed something, there may be some error. Also, wherever we've measured something, there may be some error. And there was one area where we're doing measuring, and that was in our weighing of the solids. So that values here. And what I'm going to do is I'm going to focus in on the magnesium oxide in terms of working out percentage error for weighing, because it's the smallest mass measured. Okay, so 0.921 grams. So the scales that we've got here look like they're accurate to 3 decimal place, and the guidelines with precision is that we say that whatever your resolution is, so in this case 3 decimal places, then we can go to plus or minus half a division of that. Okay, so you can see here I'm saying my precision that I can read to is 0.005. Okay, so on your scale you can read to 0.001. So I've halved that and then said, well, I can actually then say that my precision is 0.0005. Working out percentage error then gives me a percentage error weighing of 0.11% with the magnesium oxide. Just pointing out to you, why have I multiplied my precision by 2? That's because there are 2 readings. All right, so you've got your start mass and your end mass. And because you've got 2 readings, you have to multiply your error by 2. Okay, so this is something to bear in mind whenever you take a reading. If it relies on 2 readings, then you times your precision error actually by 2. Okay, so I get an error of 0.11% in terms of weighing. So what we'll look at next then is another thing that was measured, which was the temperature change. So I'm going to look at the temperature change, which had the smallest value. And that was this one here. So we're going to work with this 9.1 degrees C. So I'm just going to ask you very quickly then for you to work out your percentage error for this temperature reading. So a little pause. Okay, and hopefully then you've done the following. Okay, so look at your precision. If we look at our temperature, we're measured to 0.1 of a degree. So I've done half of that as my precision. Okay, so I can read to 0.05. And I've times it by 2 because you have a start temperature and an end temperature. And then there's the actual temperature change. The smallest one that was measured was the 9.1, and that's giving me a 1.1% error. Okay, so why do we need percentage error then? Why is it so important for us? Okay, if you look on your practical booklet, you'll see this little bit written at the front, and it tells you the number of significant figures you can quote a value to. If you look at exam papers, they'll quite often ask you, how many figures, what to quote an answer from an experiment to a sensible number of significant figures. So that comes down to working out your percentage error. So we're looking at percentage error of about 1%. And if we look here, for around 1%, so anything I'd say anything from 1 up to maybe 4%, I would go for 3 significant figures. So we can quote this value now for our enthalpy change to 3 significant figures. So that's your percentage error covered. And, you can use that for pretty much any of the experiments. The principle's the same. Okay, so just to finish off with then, here's a tricky one. It's a similar kind of thing. We've got a reaction up here that we're going to try and work out an enthalpy change for. We're going to do that using 2 other reactions. Okay, so we're not actually going to measure this one directly. We're going to measure these 2 directly and then construct a Hess cycle to be able to work out the enthalpy change for this reaction here. So what I'll do is I'll literally do a little pause moment for you to perhaps do that yourself. Okay, so hopefully you've had time there just to pause and write that down. I'm obviously going to work this through with you now. Okay, so those are the reactions. This is the one we're trying to work out the enthalpy change for. These are the reactions we're going to be using that enthalpy change using to construct a Hess cycle to be able to do that. And you see here they've quoted the enthalpy change for this reaction. We don't have a value here. This is what we're going to have to work out first of all, this delta H. Okay, so there's our reaction, and we want the enthalpy change for, and we need our intermediaries. Okay, so we need to think about, well, how are we going to construct this Hess cycle? What's going to go at the bottom? Have a quick think for yourself. What do we see that's common in those 2 reactions that we're going to be using? What's the common substance? Well, hopefully you've identified a common substance as being the sodium hydroxide. So that helps me. What I'm going to do then, because they've got sodium hydroxide in this one and this one, I'm going to put sodium hydroxide at the bottom. Okay. Right. So now we need to think about the other reaction. Okay. You can see there, or sorry, the arrow direction. So we can see here on the arrow, this is showing us that sodium oxide is reacting with water to make sodium hydroxide. So that means my arrow will be pointing down to the sodium hydroxide. As I said, direction of arrows is massively important. Okay, good. And then what we need to do is obviously think about the other arrow. Okay, so it's the direction of this arrow. So you can see it's got sodium hydroxide. The sodium hydroxide here is a reactant. So which way is your arrow going to go? Is it going to be pointing up or pointing down? Have a little reflection. And hopefully you've got your arrow pointing up. You see sodium hydroxide is becoming sodium chloride. Sodium hydroxide is becoming sodium chloride. We know that the enthalpy change for that reaction is minus 57.6 kilojoules per mole. Okay, so the long part of this question now, we've got our cycle constructed, we've got our intermediary, we've got our arrows pointing in the right direction for our cycle. We're going to work out the enthalpy change for the other arrow, this arrow here. Okay, so there's the data from the question. So use your data there now to work out various things you'll need to be able to do the calculation. Remember, we're going to be using MCAT to work out the enthalpy change, the energy change of the water. So we need the mass of solution. We're going to need the temperature change. Also, if you want to work that out as an enthalpy change, then we're going to also need to know the number of moles of the sodium oxide as well. So we can convert that into energy change per mole. So there's our values. Okay, we've got the mass of the sodium oxide is 1.24 grams. The mass of the solution. When I saw this question, I was thinking, why are they weighing a polystyrene cup? Which is kind of weird. But it's literally because, well, it's where you're getting the mass of solution from. Okay, so that's 25.75 grams, and we've got our delta T. We'll assume they've done that using their accurate method that we've discussed earlier. Right. Okay. So we've got some of the things we need. So we're going to first of all work out our energy change of the water using MCAT. I think there should be a lowercase c there, but there you go. So look at your data, and hopefully you've come up with a value of 3,767 joules. Now remember, this isn't per mole. Okay, so the next thing we're going to do then is going to convert the energy change of the water into the enthalpy change of the system. So we're going to take our Q, we're going to make it minus Q and divide by N. Okay, so you're going to work out the number of moles now of your sodium oxide. Got the data here. Okay, 1.24 grams. Okay, and that's your enthalpy change for the reaction. Okay, so we're coming out with a value of minus 188 kilojoules per mole. We can now go back to our Hess cycle, and we can see there we've got our enthalpy value on this arrow. All right, so now we're going to use our Hess law. We're going to go our alternative route, and we're going to add our values together. And if we're going with the arrow, we'll keep the sign. If we're going against the arrow, we'll change the sign. There's a slight problem though. Are we just going to add those values together when we work out delta H? There's an issue here. I'm just going to pause there and just look at that value, and I want to tell me what your issue is. And I'll give you a clue. Look at the balanced equation, or look at the equation that they've used to represent this arrow. Okay, and saying minus 57.6 joules. All right, hopefully you spotted the error. Okay, we have to multiply that value by 2. So why do you need to multiply it by 2? Well, if we look here, this is for 1 mole of sodium hydroxide reacting, okay, to form 1 mole of sodium chloride. And if we look in our reaction, it'd actually be 2 moles sodium hydroxide reacting, forming 2 moles of sodium chloride. So that value needs to be doubled. So we work out our delta H. That's what we would do. Okay. You'll notice here that the values have kept their signs, and that's because we are in our alternative route going in the direction of these arrows. So slightly different to our previous cycle. Okay, so we've done a lot there. Okay, we've looked at a year 12 prep, but it's, like I say, important for year 13. We talked about how to measure an enthalpy change, not just by plonking a thermometer in and looking at the start and end temperature, but the proper way of doing it. We've looked at how to construct cycles, test cycles. We've also looked at your percentage error, and we've looked at issues surrounding the measuring enthalpy changes using this method. So quite a lot done there. So you can see that your session 2 will be on enthalpy, which is really important for what we've just been doing, and Born-Haber cycles, which are always fun. Okay, so I hope that session was useful to you, and I'll leave you there.